So this video is on combinations and the FCP, which usually follows permutations. So just to kind of remind ourselves on what permutations are from the last video. Remember, permutations are arrangements where the arrangements of items in which the order does matter, or that the order affects the final outcomes. So for example, we had two kind of situations that happen. One where you have no repeats in your selection. So in a class of 8 students, how many ways can they arrange themselves in a line? So you have 8 students, hopefully all unique with, again, different beings. Maybe that's a clone of each other. Um, and you want to arrange them into a line, assuming that you're going to use all 8 students, because that's what the implication here is. So you have 8 spots in a line, 1, 2, 3, 4, 5, 6, 7, 8. And we want to figure out how many different ways can we put these 8 students in these 8 spots to make that line there. And we have this formula, n factorial over n minus r factorial, where n is the total number of people you have, and r is the total number of people you're picking, or things that you're picking from that n. So in this case, my n was equal to 8, and my r was also equal to 8. Now, it doesn't always happen that they're the same, but every now and then they are. Um, and in this case here, the formula was abbreviated as NPR. So this would be 8 pick 8, which as a fraction would be 8 factorial over 8 minus 8 factorial, which would be 8 factorial over 0 factorial, which we said in the last video, 8 factorial over 0 factorial is actually just 1, which is just 8 factorial, which if we do in our calculator, we do 8 factorial, and we get 40, 32, 0. So 40, 32, 0. And that'd be how many different ways you can arrange these 8 students in the line there. Again, in this case, the order does matter, because if I put Billy first, that's going to be a different line than if I put, say, Billy second. So again, the order in which you put them does change the actual outcome. It makes a different line, a unique line compared to the others. Now, if you have repeats in your selection, which usually had letters involved, where you say you take a bunch of letters, like in this case, Paulus Math, so excluding the space there, how many different ways can you rearrange these letters given this set? Well, we start with pretty much the same formula, except that because we have repeats, we can't just use NPR. We have to kind of do it by hand. So n is still a total number of things that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 letters, so 10 factorial. And then the n's down here are basically the number of times each unique letter repeats. So for example, P doesn't repeat at all, so I can just basically ignore that. So P doesn't need to be adjusted. A here repeats twice, so I'd put 2 factorial down here to represent the fact that my A's repeat twice. And the same for my U's. My U's repeat twice, so I put a 2 factorial here to represent the fact that my U's are repeating. L, S, M, T, and H all don't repeat, so I don't need to worry about them. So this would be what I have here, and this would be how I would get my answer. So I would do 10 factorial, math factorial, divided by 2 factorial, which is really just 2, but I'll write it out here. 2 factorial times 2 factorial. And I get 90, 7200. So 90, 7200. Just to make sure I got that right. Right. So, whoops. So, 907,200 different ways that you can arrange these letters, again, after you factor out the repeats. So, again, those are where the order does matter, that if you switch the first and the second thing, you get a new unique outcome that's different than the one you had before. And those are called permutations. Well, what if the order does not matter? So put another way, if I pick the letters A, B, C, and that's going to be no different than picking, or instead of saying letters, let me say option. If I pick option A, then option B, then option C, if that is no different than picking C, B, and A, then I have a combination, because I can switch around the order of things and it doesn't really matter. The best way to think about this is usually in terms of food, believe it or not. So we have an ice cream company that sells these different flavors of ice cream. So we have 1, 2, 3, 4, 5, 6 different flavors of ice cream. A customer gets a triple scoop, with each scoop being a different flavor, so they don't double up on the category. How many different combinations can they make? Well, that means that if I pick any three flavors, if I pick them in a different order, it's not really going to change my outcome, right? I'm still going to get those 3 scoops of my ice cream. So if I pick, say, macadamia, strawberry, and green tea, if I pick those as my flavors, and then I go back and say, well, I want green tea, strawberry, and macadamia nut instead, that's the same order, just said differently. So it's really not affecting the outcome. I'm still going to get all 3 flavors in my scoop. It doesn't matter. One might be on top and one might be on bottom, so that might be different, but the actual outcome in terms of what I get as my order has not changed. So think about them as putting it into a bowl rather than into a cone, if that's going to make more sense to you. So if I have a bowl of ice cream and I put a scoop of macadamia, a scoop of strawberry, and a scoop of green tea, that's going to be no different than a bowl and I pick a scoop of strawberry, a scoop of macadamia, and a scoop of green tea that way. The order in which I put them in the bowl does not matter. I'm still going to get a bowl with those 3 flavors. So we still have the same N and R. So N is still a total number. So that's the total number of options we have. So total options. And then R here is the number that we pick. So number we pick. So that's the number symbol. So R is the number that we pick, N is the number of options that we actually have available, and the formula is this here. In fact, if you look closely, it looks pretty much almost the same, right? This part right here, that right there is actually NPR, just that piece. This extra little R factorial makes it a combination because this divides out all the repeats. So this little R squared is there to make sure that A, B, C, C, B, or C, A, B, B, A, C, dot, dot, dot. Make sure that all those are not counted twice or 3 times or 6 times or whatever. So that little R factorial there makes sure that it counts all of this as just one outcome. So again, macadamia, strawberry, green tea, strawberry, macadamia, strawberry, green tea, macadamia, all those are the same order. And so I don't want to count those more than once, which is what that R factorial down here does, is it divides out all the repeats. So in this case, I have, what do we say, 6, right? 1, 2, 3, 4, 5, 6. So I have 6 flavors. And I'm going to pick 3 because it's a triple scoop. So 1, 2, 3, 4, 5, 6 flavors. I pick 3. So I would have 6 factorial. 6 factorial over 6 minus 3 factorial times 3 factorial, which should be 6 factorial. 6 minus 3 factorial is just going to be 3 factorial times 3 factorial, which is not 9 factorial, by the way. These are done separately. So if I go back to my calculator here, if I go back up, again, it looks very similar to the permutation one with repeats on it almost, right? So I have 6 factorial, 3, and 3, and I end up getting 20. So there's 20 different combinations that I can pick if I pick 3 flavors from these 6 here. 20 different ways I can get my order there. Because again, doesn't matter what order you put them in, you're still going to get that as a result. Usually combinations are a lot less than the number of permutations for the same number of items. So if I have 5 options and I pick 2 of them, my number of combinations is going to be a lot less than my number of permutations. Because remember, combinations divides out all those repeats, whereas permutations do not. So let's try another basic one here, again, usually with food because it's the easiest to visualize. So put this down here. So we have a pizza store running a special on a large 2-topping pizza, and it has the following toppings. So it has 1, 2, 3, 4, 5, 6, 7 toppings, and you pick 2 because it's a large 2-topping pizza. How many different combinations can we have? Okay, well, we have 7 options, and we're going to choose 2 of them. So that's usually how the formula is written, 7C2, just like the other one was 7P2 or NPR. This is NC. Whoop, let me try that again. One more time. Oops. There we go. Not sure what happened there. So this is NCR, just like the other one was NPR, or sometimes this is even written like this. 7 choose 2. So this notation is the same as this notation. They all mean the same formula of n factorial over n minus r factorial times r factorial. These all 3 mean the same thing. They're just different notations for the same reasoning. So for me here, 7 factorial options, 7 minus 2, because I'm picking 2 of them, times 2 factorial, because I want to divide out the repeats, And so if we write that into our calculator here, that would be, going back here, so that'd be 7 factorial on top. 7 minus 2 is 5 factorial, and then 2 factorial right here, and I get 21. So I have 21 different options for this uh, large 2-topping pizza here. I have 7 choices. I'm going to pick 2 of them, so I have 21 different possible combinations I can make. Because again, if I pick a pizza with cherries and Cheetos versus picking a pizza with Cheetos and cherries, it's the same thing, right? It's the same toppings. So I only have 21 different combinations. If I wanted permutations, then I would count those two as different. So a permutation would be saying that Cheetos and cherry topping is different than a cherry and Cheetos topping, which again doesn't make any sense, which is why it's a combination problem, not a permutation problem. So let me find out where I am here. There we go. So one spot of difficulty that people often has here is knowing when something's a combination and when's a permutation. And again, the main thing you want to keep in the back of your head here is that permutation, the order does affect the outcome. So if you can switch your first and your second pick and get a different, meaningfully different, I should say, a meaningfully different result, then it's a permutation. If you pick your first and your second option and you switch them and it does not give you a meaningfully different result, then it's a combination. So again, if I have, let's say, 3 options of ice cream, if I have chocolate, strawberry, and vanilla, and I get to pick 2 of them for a double scoop, let's say. If I pick chocolate and strawberry, that is not meaningfully different than picking strawberry and chocolate. So these are basically the same order, essentially. So this is that would be a combination type problem because when I switch the first and second pick, it does not give me a meaningfully different result. Whereas if I'm saying putting people in a line, let's say this was Charlie, Sue, and Van for names. I'm not sure what a name starts with a V, or Vince. We'll say Vince. So Charlie, Sue, and Vince. If I'm picking 2 people and I'm making a line with 2 people, first and second spot, well, picking Charlie and Sue as to form a line is going to be different than a line that has Sue and Charlie. So this line is actually meaningfully different than this line because in here Charlie is first, which is kind of a special, again, privilege. It's a meaningful result here, whereas in this case Sue is first. That's a meaningful difference in the position of students. Whereas picking flavors, it's not really meaningful because you're going to get the same 2 flavors. So let's look at a few of these here. So in a group of 7 members, how many different ways can a group of 4 be picked to give a presentation to the administration? So we're picking 4 people from this group of 7 to give a presentation. So if I pick 4 people, let's say I pick, again, we'll say Abby, Becky, Cindy, and Doug. So Abby, Becky, Sydney, and Doug. Is that different than me picking Doug, Abby, Sydney, and Becky? Is that any different? Well, not really, because it's still the same 4 people giving the presentation. So this is a combination problem, because if I switch up the order, then I still have the same 4 people going. So this would be 7 choose 4, not 7 pick 4, because again, the combination means that if you switch them, there is nothing that's meaningfully different. So these 2 are not meaningfully different to each other. So in your calculator, you can actually do that with the notation here. So 7 math, go over to probability, there's your NCR, choose 4, and you get 35. Whoops, I already put the equal sign there. So equals 35. So again, switching the order here is not meaningfully different. Whereas down here, same group of 7 people, but you're picking 1 person to be treasurer, 1 person to be officer, and 1 person to be butcher. How many different ways can these positions be filled? Well, if I pick Abby, Becky, and Sydney, so treasurer, officer, butcher. Well, if I pick Sydney, Becky, and Allie, that'd be treasurer, officer, butcher. So that is meaningfully different because in this case, Abby is treasurer, whereas in this case, Sydney is treasurer. So this is a meaningfully different result. So the order does matter. So that'd be a permutation or 7p3 in this case because I'm picking only 3 people in this case. So this again, if you switch around your picks, you get something that's meaningfully different. So 7 pick 3 and we get 210. So again, do a test case. So if you're deciding between combination or permutation, do a test case. switch around the first and the last pick, or the first and second pick, or the second and last pick, I don't care, but switch around 2 positions and see, does this give me something that's meaningfully different? If it is meaningfully different, then it's a permutation. If it's not meaningfully different, then it's a combination, because in that case the order didn't matter. So let's see if we can't tell a few more here. So we have using standard digits 0 through 9 and assuming no restrictions, how many different 7-number arrangements can be made for phone numbers? Now, phone numbers actually do have restrictions on what numbers can be put where, but assuming there were none, if we have 7 digits for a phone number, so 1, 2, 3, 4, 5, 6, 7, how many different 7-number arrangements can we make from this? So again, is this a combination or permutation question? Well, in this case, let's pick a number here. 1, 2, 3, 4, 5, 6, 7. So you type in that number, you call it number, and let's say that connects you to Mr. Paulus. Okay? So that's Mr. Paulus's number. So if you go on the phone and you switch around 2 numbers here, so you make it 2, 1, 3, 4, 5, 6, 7, and you call that number, would that still get you to Mr. Paulus? Well, no, it wouldn't. It'd get you to somebody else. You typed an entirely different number. You can't have one person have, if you type in the different 7 numbers, you're going to get a different person on your phone number. If you don't believe me, you can try it yourself. Dial somebody you know, and then switch the first and the last digit of the number you dialed, and you're going to get somebody different, or if not, an error. So this case, this would be a permutation. So this would be an NPR problem. And the reason it'd be an NPR problem is because the order matters. If I switch 2 numbers, I'm connecting to a different person than I was originally. So phone numbers are permutations because the order in which the numbers occur do matter. In this case down here, we have a sandwich shop that's offering 5 selections of meat, and you get to pick 3 of them to make a sandwich. Would that be an NPR or NCR question? Well, again, if I order a duck, quail, and veal sandwich, is that going to be any different than if I ordered it as veal, quail, and a duck sandwich? Well, no. I mean, the order of the meat might be different, but when I bite into it, it's still going to be a duck, quail, veal sandwich, no matter what order they come in. So this would be an NCR question, because if I switch the picks here, it doesn't really give me a meaningfully different result. Yes, the order of the meat might be different in my sandwich, but am I going to notice that? No. So that would not be a meaningfully different result is what we're talking about there. And then what about this last one here? So a dog show has the following dogs, 3 retrievers, 2 poodles, and 4 shepherds. 1 dog from each breed is to be selected for the show. How many arrangements are there? So we're going to pick 1 retriever, 1 poodle, 1 shepherd. How many arrangements are there? Is this a combinations or permutations questions? So this is, again, kind of tricky here because we have different categories, not just one category to pick it from. We actually have different categories. We have 3 options for retriever, 3 options for poodle, and 3 options for shepherd. And we want to figure out how many different ways we can pick it. So, we could pick, say, Alice for retriever, we can pick Susie for poodle, and we can pick Moira for shepherd, or we can pick Alice for retriever, Suds for poodle, I'll put SU for Suds, and Ralph for shepherd. So there's a few different ways we can arrange it. So this is kind of a weird problem here. Is it a combinations or is it a permutation or is it kind of a mix between the two? And so this is the type of problem we're going to be looking at here in the next case. So let's go ahead and take a look at it. So every now and then, like with the last problem, we need to kind of use this combination and permutation formula in sort of creative ways. So let me show you one way we can do that here with this problem. I'm going to switch it up a little bit from dog breeds here just to show a little bit more clear about what's happening. So let's say we have a club. We have 6 members that are seniors and 13 members that are lower classmen, so freshmen, sophomore, and juniors. A committee is formed from the club, and it's going to be made of 4 senior members and 2 lower classmen members. And we're going to assume that, again, it's just a committee. So if you get picked first, it's no more special than if you got picked second. How many different committees can be made? Well, in this case, we're going to basically treat this as 2 different combination problems, one for seniors and one for lower classmen. So for instance, in this case, we figure out, okay, how many ways can we choose 4 seniors from 6? Now, this is a combination question because, again, it's a committee. So if I pick Abby, again, Becky, Cindy, and Doug as my 4 seniors, is that any different than picking Doug, Abby, Becky, and Sydney? Well, no, because either way, whether you're picked first or second, you're on the committee. I didn't say you're picking positions, so it's not like treasurer, president, or anything like that. It's just, are you on the committee? So this is a combination situation because, again, the order does not matter. So I have 6 seniors, and I want to choose 4 of them. So NCR, 6 choose 4. So if we do that real quick, 6 choose 4, we get 15. So there's 15 ways I can choose my seniors. Then I figure, okay, how many ways can I choose my lower classmen? So I have, again, same situation. 13 lower classmen, I'm going to choose 2 of them to be on the committee. So 13, choose 2, and I get 78. So there's 78 different ways I can choose my lower classmen because there's quite a bit more of them. So the way I would get my total number of combinations, the way I'd end it, come on. The way I end it here is I would do 15, which is the number of ways I can choose my seniors, times, not add, but times 78, which is the number of ways I can choose my freshmen, or my lower classmen, I should say. And so I do 15 times 78, and I get 1185. So there's 1,185 different ways I can pick 4 seniors from 6 and 2 lower classmen from 13 to be on this committee here. So you kind of had to break it down into, again, 2 smaller problems and then multiply it together at the end, which is basically how you would do this one here. Whoops, my bad. How you would do this one down here. So it is a combinations questions, but you'd say, okay, I'm going to choose 1 from these 3, 1 from these 2, and 1 from these 4, and then multiply them together, which actually is a relatively simple problem because if you're picking 1 from 3, well, how many different ways can you pick one thing from 3 things? Well, there's 3. I can either choose Alice, Bill, or Buddy. So that's 3 different ways there. Susie or Suds. That's 2 different ways there, and then 1, 2, 3, 4 different ways there. So because I'm only picking 1 from each category, it's a fairly simple procedure, but it's still the same idea. 3 choose 1, 2 choose 1, 4 choose 1, and then multiply it all together. Whereas here, it was 6 choose 4 and 13 choose 2. So that was a little bit more difficult because you had more options to go from rather than just picking one person. So again, if you have this case here where you have a bunch of different categories and you're picking from a different pool for each category. So seniors, I was picking from this pool of people. Lower classmen, I was picking from this pool of people. Then break it into 2 separate problems. And lastly, we have this thing called the FCP. So the FCP is kind of like a modified permutation rule. So what the FCP, or fundamental counting principle, is, basically says if you want to find the total number of arrangements, then multiply the total number of items for each spot together. So let me give you an example here. A school has 3 teachers in its math department, 5 in its English and social studies, and 4 in its science. If each department is to select a representative and an alternate to go to a conference, how many different possibilities are there? So this case, this is kind of like a permutation version of the last one we just did. So this was a this one was a combination questions or combination question rather, because the order didn't matter. These 4 seniors can be picked in any order they want. It's going to be the same set of 4. Again, if I change around the order, it doesn't matter. Whereas in this one here, the order does matter because this person is going to be my main representative and this person is going to be the alternate. So this person has a special little unique privilege to it that this one does not, and vice versa. This one is actually going to go unless they get sick. In this case, the alternate goes. So this is a backup. This is the intention. So this is, again, representative, alternate, representative, alternate. So because it's a permutation question, we don't use NCR, we could use NPR, but there's actually an even easier way of doing this. Because if I have 3 math teachers, and I want to pick an alternate and a representative, well, that means that any one of these 3 can be my representative. So I put 3 there. Any one of the 3 math teachers can be my representative. So this is for math here. Now, whoever's being the representative cannot also be the alternate, obviously, right? I can't be the representative and the alternate. I have to have a different person be the alternate. So if I pick I can pick 1 person from 3 for this spot. And then that means I have 2 people left that can be my alternate, right? So one of the 3 is going to be my representative, and then one of the 2 is going to be my alternate. And then for the English and social studies, so E/SS, they have 5 teachers, right? So how many of these, again, using the FCP here, what's the total number of these that can go to my representative spot? Well, 5 of them. 5 teachers can be one of my representatives. Well, now that I pick that person, how many are left that I can put in the alternate spot? Well, 4 of them, because again, I can't have the same teacher be the representative and the alternate. And then same thing for science here. So how many people can I pick to fill the representative spot from the science department? Well, there's 4 teachers, so any one of the 4 can be the representative. And then that means there's going to be 3 left to choose from to be the alternate. So again, you do it slot by slot. You have a math spot, an English social studies spot, and a science spot, SCI, and you just figure out how many can go in each slot one by one by one, and then you just multiply them all together. So times them all down the road there. So 3, 3 times 2 times 5 times 4 times 4 times 3, and you get a grand total of, come on, 1440. And that would be how many different arrangements you can make there. And again, this is a permutation type question because the order in this case does matter. If I'm picking Mr. Paulus to be the representative and some other person to be the alternate, that's going to be different than some other person being the representative and Mr. Paulus being the alternate. That switch there has an impact. So unlike the other one, this is a combination question that had I guess you can call this a compound combination question because you had 2 different combinations you had to work with. Whereas this was more of a compound permutation question because you had 3 different permutation cases you had to work with, essentially. So that's it for this video. Again, it's a little bit of there's a little bit a lot to digest there, so don't be afraid to rewatch this video or certain parts of it if you need to. And as always, let me know if you need any more help. Hopefully you enjoyed this and helped you out. Have a good day.